multiplication counting principle is in section 7.3. Let's suppose you're in a situation where you have you're designing some outfits. You have 3 shirts to choose from, 4 pants, 5 pairs of socks. How many different outfits can you come up with? Well, this is just multiplying them together. 3 times 4 times 5. We end up with 60 different outfits when we multiply 3, 4, and 5 together. So that's as difficult as the multiplication counting principle gets, and we can use that in a variety of different ways. We talk about situations which are selections with replacement. How many different ways of answering 5 true-false questions? Well, you can think about it as 5 different questions, and you can think about the number of possible answers for those 5 questions. For instance, I've got 2 answers for the first choice, true or false, 2 for the second, 2 for the third, 2 for the fourth, and 2 for the fifth. And so when we say selections with replacement, what we're saying is if I use a true on the first question, it does not mean that I can't use true on the second question. Selection without replacement would be once I used an option, then it was gone. Kind of like matching. So true-false falls into the with replacement category. 2 to the 5th is 32. So there's 32 different possible ways we could answer those 5 true-false questions. Now, what's the probability that I get them all correct? It is not the same question as what's the probability that you get 1 or 2 or 3 correct. I know I'm on the average going to get some correct. In fact, the average would be what? Well, the average, you got a 50-50 chance, right? So 2.5. I should average 2.5 correct answers if I would do it repeated times. Obviously, I can't get 2.5 in a single try. So what's the probability of answering all 5 correct? Well, out of those 32 different options, only one of them has all 5 correct answers. There's only one right answer key. So the probability of getting them all correct is 1 out of 32. Now, what happens if we talk about multiple choice? I've got 5 multiple choice questions with 4 answers. So 1, 2, 3, 4, 5. I've got 4 answers for that one, and 4 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 for that one, giving me 4 to the 5th. Well, 4 to the 5th, what do we got there? 16, 64, 256, 1024 is the number of possibilities there. What's the probability of getting them all correct? Well, there's only one right set of 5 correct answers, and there's 1024 different ways of answering those, so the probability of getting them all correct is 1 out of 1024. Now, my assumptions on these are that you are purely guessing. For instance, let's suppose these 5 questions were from a graduate level engineering exam written in Chinese. Then I think you'd probably be guessing. All right? How about 6 multiple choice questions with 4 choices and 5 true-false questions? So you'd have 6 multiple choice questions with 4 answers apiece and 5 multiple choice questions with 2 answers each. So we need to multiply these 2 together in order to come up with our overall answer. All right, so 4 to the 6th power times 2 to the 5th. So there's 131,072 different ways of answering that particular question. Now, obviously, if you're guessing, there's only one correct answer, and so if you wanted to get all 10 questions or all 11 questions correct, you would have to, there would only be one way out of those to just purely guess. So purely guessing is not a very good option. It'd be better to study, you know. All right, so what about selections without replacement? Selections without replacement. Sorry, I started running out of room, so that's why it looks all crammed in there. Selections without replacement. Well, suppose you want to rank your top 5 college choices. So for slot number 1, your very first pick, you have 5 different options. But once you select that college choice, there's only 4 selections for your second favorite, and 3 selections for that one, and 2 selections for that one. And the last choice you have doesn't really have an option. So this is still the multiplication counting principle, but because I'm not allowed to put one back in, I can't put all 5 of them being the same choice. There's no replacing. So this is 5 times 4 times 3 times 2 times 1. 24 times 5. I think that's 120, but I'm just going to check it. Yeah. So we have 120. Something called factorial. Now, when you go to parties and you want to read this number, you want to read 5. I know, I just blew your eardrums out. I was very excited about it. I saw the exclamation point, right? Thinking in my English class they taught me about emphasis, you know, and just trying to convey that through the medium of YouTube. So let's see here. 5 factorial means I start with the number 5, and I want the product of that times each of the integers below that, all the way down to 1, which is exactly the same thing we just did. So 5 factorial, if you've got your calculator, hopefully you got it handy somewhere. You want to type the number 5, and then go to the second stat button. Okay, so I use the second button and then the stat button. Then I go over to math. Oh, I'm in the wrong spot. Clear that out. So we still got our 5. It's under the math button, right? Right here, the math button. If only your math teacher knew what he was doing. Okay, then PRB over on the far right. And then you'll notice the fourth one down is the factorial button. All right, so I hit the enter button for that. 5 factorial 120. There we go. So now you can do your factorials. And the definition for factorial, something we need to practice with a little bit, is n times n minus 1 times n minus 2 times n minus 3, all the way down to 4 times 3 times 2 times 1. I know, I can hear you all right now. Well, MrJStailey, I thought you were supposed to count down. I thought you were supposed to start with the integer and count down. But clearly it looks like you're counting up. Okay, keep in mind there's a negative sign right there, so when you're subtracting a larger number, the other number gets smaller. So let's just suppose this was a 17. 17 factorial. That would be 17 right here. 17 minus 1 would be 16. 17 minus 2 would be 15. 17 minus 3 would be 14. And so on. Eventually I'm going to get down to the integers 4, 3, 2, and 1. I know many of you think I'm counting up, but I'm not. I'm counting down. Now, keep this in mind. This is the number of possible arrangements of n elements without replacement. The number of possible arrangements of n elements without replacement. Okay? That's what factorials are. I bet we can do this one without a calculator. Well, if you understand the definition now, I know those of you who reached for your calculator right now and you're typing 122 factorial, the calculator is saying error overflow, and now you're panicking because you're like, what do you mean I have to do that without a calculator? I can't do that kind of multiplication. I can barely reach 100. Well, understand what you got. 122 times 121 times 120 times 119, all the way down to 3, 2, and 1. And on the bottom we have 121 times 120 times 119 times all the way down to 3, 2, 1. Does anything cancel out? Well, of course they do. The ones. Ha ha ha. And the 2's and the 3's and everything up to 121 cancels out, leaving me 122. That was such an easy question. Only if you know your definition of factorial. Otherwise, you're panicking. All right, so what about this? I've got n times n minus 1 times n minus 2, dot, 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 dot. Oops, sorry. N minus 3, n minus 4, dot, dot, dot. All the way down to 3, 2, 1. What do you got on the bottom? N minus 2, n minus 3, n minus 4, all the way down to 3, 2, 1. Anything cancel out? Sure, a ton of stuff does. The only thing left is n times n minus 1. That's it. What about the next one? We got n minus 1 times n minus 2 times n minus 3, dot, 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 3, 2, 1. N plus 1. One smaller than that would be n. One smaller than that is n minus 1, n minus 2, n minus 3, all the way down to 3, 2, 1. Anything cancel out? Sure, from n minus 2, n minus 1 on down, everything cancels out. Now, keep in mind, folks, please notice that if you cancel all the factors out of the numerator, 1 will be there. He's a nice guy. Don't forget about it, okay? 1. He's important. Very, very important. Whoops, too far. So my answer to this is 1 on the top and n times n plus 1 on the bottom. One on the top and n over n plus 1 on the bottom. And that concludes my